All right, problem number 6, last one on this set. Another slope field, another Euler's method. So third time this week. Cross my fingers, hope Euler's method shows up for you. Maybe I'll put it on my final just since I've done it enough. Hopefully it shows up on the AP test. We won't see it very much in the rest of our practice, but it's a pretty common thing. You can see I just picked 3 years at random, and you get lots of different Euler methods problems. So you got this slope field again. Derivative is 2x minus y. I drew that slope field, so it's very, very rough. Remember, you're just plugging in points. So I'm going to pick this point right here. Like that point's 1, 2. So I plug in 1, 2 minus 2 is 0. Hence the slope is 0. So you're just drawing in those slopes as best you can. They're just going to look for some key ones. 0, 0. They're probably going to look for that one, just relationships. They ask you to draw the curve that goes through the point 0, 1, which is right there. So it's got to go through that point, so I don't know, roughly something like this. It's going to bounce up like that. Keep in mind, just for the last problem, because I'm not going to come back to this, that we need the fact that that red curve is above the x-axis, so y is positive. Y is positive. It's going to come back up again in the last part of the problem. So that's part A. Part B says the solution curve, this curve, has a minimum at x equals the natural log of 3/2. Natural log of 3/2, about right there. Find the y-coordinate. So if it has a minimum value at that point, that means the derivative has to be 0, right? So 2x minus y has to be 0. Pretty straightforward. They told me what x was, the natural log of 3/2. So 2 times the natural log of 3/2 minus y has to be 0. So y has to be 2 times the natural log of 3/2. Euler's method. I'm going to go through this really quickly again. The only difference in this one, the Euler method, is we started it at 0 and we were going to negative 0.4. So we're moving to the left. So when you're moving to the left, your step size has to be negative. And all the other Euler's method problems you've seen me do or seen on the solutions, that's a plus sign, but now it's a minus sign because we're going to the left. So I started with the 1, subtract the step size. We're going from 0 to 0.4 in 2 steps, so the step size is 0.2. Subtract that 0.2, you're plugging 0, 1 into this. Plug 0, 1 into this, you get negative 1, you get out 1.2. So now I'm at the intermediate step of negative 0.2, 1.2, same thing, take that 1.2, subtract the step size, plug in the negative 2, 1.2 into this, that's my work you see right there, and you get 1.52. So third time for Euler's method, cross your fingers. I hope you're good at it. If you've been practicing, you should be. I hope it shows up. And then the last problem on this set says find the second derivative. So the second derivative is pretty straightforward. Here's the first derivative. Second derivative is the derivative of this. That's 2 through that minus through that, which is y prime. But y prime is that, right? dy dx. So 2 minus 2x minus y says 2 minus 2x plus y. And then it says determine whether your approximation last part was less than or greater than negative 0.4. So again, remember that approximation. Even though it doesn't really say it, Euler's method is using a tangent line. So what we're asking for is concavity. Concave up, tangent line under approximates, there's too low. Concave down, it's too high. So I take the second derivative and I plug in that point, negative 0.4, into this. So 2 minus 2x plus y, so I get 2 plus 0.8 plus this y. Here's the catch from before, remember that. I don't know what y is, but I do know we're on that curve that goes through the point 0, 1, so it has to be above the x-axis, so y has to be positive, which makes this number positive. So the second derivative is positive, means it's concave up, which means the approximation is too low. So you notice this concavity idea with approximations. You've seen now 4 or 5 times is your approximation too high or too low. Pretty much any time in this class we do an approximation, it's a tangent line approximation, unless it's a series, that's a whole different thing, but it's a tangent line approximation, and the too high or too low is based on its concavity, second derivative.